So again, thanks Eric, not just for your Lys introduction, but also for bringing me to the lipid world and the AOCS family. So I attended my first AOCS meeting back 11 years ago. It was in Phoenix, Arizona. So after that, I got to know lots of friends and the outstanding researchers through the AOCS meeting. So they are always inspire me in many ways. So I'm also very grateful for the award committee and AOCS to give me this award. So it means a lot to myself and also to my research program here. So that I'll have a chance to share a series of research we've done on the protein-phenolic conjugates with you today. So in addition to the traditional lipid research we've done here, so in my lab, we also expanded research into the protein-related research. So the major reason is the university I'm working at, the North Carolina State University, it's an agriculture-based university. So we have a chance to work with all kinds of the commodity products. And here the pictures at least will be the major commodity products I'm working on right now. So why am I so interested about the dual functional food ingredients? So this will go back to the papers I read a couple of years ago. So by that time, so I understand food waste is the major cause to impact the food security and the sustainability. But before this year, we only have the general concept about food waste. Start from this year, so the United Nations has developed two different index. So one is food loss index, one is a food waste index to specifically describe the waste in the whole food systems. And there are so many reasons that will contribute to the food loss and waste. For the food scientists, we are always targeting the microbial spoilage caused the lost waste and the chemical food spoilage related food waste. So as a food chemist, for myself, my major interest is about the lipid oxidation. And it is also one of the reasons causing the food loss and waste. So if you attend Dr. Decker's award presentation early this month, so you will still remember lipid oxidation will be still the biggest challenge in the food industry. Part of the reason is nowadays consumers want to have more health ingredients and bioactive compounds in their diet. Example is they want to replace the saturated fat by the healthier polyunsaturated fatty acids in their diet. But this kind of the trend will inevitably promote the oxidation of the food, which will cause the loss and a lot of other issues. So the smart food scientists have found the low cost and synthetic antioxidants to be the very good strategies to prevent or retard the lipid oxidation in the food system. However, again, so consumers want to have natural ingredients for their food products. We know in nature, we are able to find lots of the natural antioxidants, as I demonstrate here. But among them, very few of the antioxidants have been applied in the food formula. A very good example would be the rosemary extract. So it has a very good antioxidant capacities. So when I joined NDSU, I started to look at the antioxidants from the cereal and pulse grains here. So that is the start of the journey. So today, I'm gonna just share three separate researchers with you so that you understand our journey from this natural inspired synthesis of the dual functional food ingredients. So we start off the research from the pulse grain germination. So pulse grain basically it includes chickpea, lentil, yellow pea, and other dry beans. So pulse grains has lots of the health benefits. One particular one is it has high dietary fibers. So if you take a look at the microstructure of these pulse grains here, so the image here, that's a confocal image we took from our lab. So the green one here, so that's a cell wall in these cotyledon structures. So cell wall is the major is consisted of the dietary fibers, and it is also the good reservoirs for the phenolic compounds. for all those phenolic compounds, they can be divided into soluble phenolic compounds and insoluble bound phenolic compounds. So the soluble phenolic compounds can be further divided into soluble free and soluble bound. So those soluble bound will be the phenolic compounds conjugated with, for example, those dietary fibers, for example, like pectins, anaerobic xylons, and beta-glucan, those types of the hemicellulose. So in fact, in the pulse grains, the amount of the phenolic compounds is relatively low compared to other like the fruits or vegetables. Germination, a traditional natural biotechnology, has been proved to be an effective way to improve the amount of the phenolic compounds in these grains. However, there are very few of the research trying to understanding how the germination will impact the structure and the phenolic compounds and also their antioxidant capacities in the food system. So during the germination, we know lots of enzymes will be activated. So those enzymes could hydrolyze the bonded phenolic compounds to release them as a free form. So also they will have some new phenolic compounds synthesized during the germination because they will be used to attack the free radicals generated. So have that in mind, we designed a series of this research on this germination, the pulse germination. So here is the flowchart demonstrating our design. We selected 3 different types of the pulse grains, chickpea, lentil, and yellow pea, and we germinate all those seeds under the controlled conditions over the course of 6 days. And then we freeze dry them, extract the soluble free and soluble bound portions, and then we evaluate their antioxidant activities using in vitro assays and using the stripped soybean oil in water emulsions. So after that, we characterize the structures we extracted. So we collect a lot of the interesting results, but here I just want to show you very significant results we found. The table here shows you the antioxidant activity of the phenolic compound extracts during the germination, and we found the soluble free portions, they have relatively low antioxidant activity against the emulsion oxidation. But for the soluble bound one, in general, they have higher efficacy compared to their soluble free portions. And the type of the grains has significant impact on their antioxidant capacity. So for example here, so chickpea we found with the germination, the soluble bound extract increased their antioxidant activity. And yellow pea is on the other side, so it decreased their antioxidant over the course of germination. The graph on the right side here demonstrates the example from yellow pea. So the bottom 2, that's the oxidation study for the soluble free extracts. So you can see they have a very, they have 4 days of lag phase to prevent the oxidation of this stripped soybean oil emulsions. So the bottom 2 shows you the oxidation kinetics of the soluble bound extracts. So they have a longer lag phase. However, the bottom line here, you'll see that's the kinetics for the extract without germination. So with germination, actually, it decreased their antioxidant activity. So that will be the major findings we have. Since, like I mentioned, chickpea has a very interesting effect on the antioxidant capacity. So we then analyze the structure of those phenolic compounds from different fractionations using the high resolution Q12 mass, and we also characterize the structures using other technique. So by using the chemometric analysis, it tells us that, so CB here stands for the chickpea bound. 4 means like 4 days of the germination. We found that like the longer germination time separates the fractions with the rest of the compounds. And further identify the compound on the right side, you can see we identify like 3 compounds that is the major compounds differentiate their roles with the others. So among them, we found like gentisic acid is phenolic acid is 1, and we also found flavanones, these compounds. So those will be the major finding we found. And here I have a short conclusions for this part of the research. We found like germination in general, it could improve the total phenolic compounds. So that is in line with most of the studies. And we also found like germination has different roles on the antioxidant activity of the different portions. So for the soluble bound one, like I said, chickpea, the soluble bound phenolic extraction from chickpea, so they have better antioxidant capacities with the extended germination. However, for the yellow pea, it has an adverse effect for their antioxidant capacity. And also we found the soluble bound phenolic compounds has a better antioxidant activity against the emulsion oxidation than the soluble free ones. Along with other like characterizations, we propose a dual effect mechanisms for the improved antioxidant activity for the soluble bound phenolic compounds from the chickpea. So we assume like they are coming from two parts. One is from the phenolic compounds itself. Another one will be the substitute these phenolic compounds conjugated. So by that time, we then applied what we call like a reverse thinking strategies. We thought, is there any way we could like build up these types of the conjugate compounds by attaching phenolic compounds on another food biopolymers? Then this brings us to our next levels of the studies. We want to stick with this genetic acid and then finding another food biopolymers. So the second part of the study, then we choose β-lactoglobulin as these food biopolymers. So why do we want to use this β-lactoglobulin? Number one, so this β-lactoglobulin is a very excellent food emulsifier. It has been widely used in the food industry. So Dr. Decker's previous study also indicated that β-lactoglobulin has a mild antioxidant capacities. So this is a relatively small globulin proteins with the molecular weight of 18 kilodalton. So there are several ways we can conjugate the phenolic compounds on the protein. So we choose a chemical coupling reactions. The reason is, so for the β-lactoglobulin, it has 162 amino acids. Among all those amino acids residues, lysine has a very high abundance. It has 15 lysyl residues. And then we choose a very classical bioconjugation coupling reactions using EDC and NHS coupling reagents. So the principle of this coupling reaction is to use these coupling reagents to activate carboxyl groups from the phenolic compounds so that they will have amide reactions with the amine groups from the lysyl residues. So using this kind of the coupling strategies, we are able to control the reactions, and we will know what exactly the reaction site is. So the research plan is very common. So we synthesize these compounds, and then we characterize the structures and understand their activities. Since this is the totally new reaction systems, nobody has done this with the genetic acid, although this coupling reagent is widely used for bioconjugation synthesis. So we start off with optimizing the EDC and NHS reagents, more ratios with this genetic acid. You can see the chromatograph on the right side. That's the strategy we use to optimize these reactions. The peaks on your left, so that's the peak from the genetic acid. When we increase the amount of the EDC from 1:1:1 ratio to down to 1:3, 1:5 to 1, you can see the peak for the genetic acid is disappeared. And on the other side, you get a new peak. So that's the intermediate for these coupling reactions. And then we decide to use the 1:5:1 ratios for this genetic acid and coupling reagents. So following that, we want to know how the fitting ratio between the genetic acid and β-lactoglobulin on the structural properties. And so we design a series of the synthesized strategies by setting the ratio between the genetic acid and the β-lactoglobulin as 1:5, 5:1, 10:1, up to 300:1. So very common. So we characterize the structures of these synthesized compounds using the FTIR. So here I just want to point out a new absorbance at around 140 here. So we assign this one to the hydroxy groups stretch from on the genetic acid compounds. So keep this peak in mind because I'm going to bring this one back later. And then we use the high resolution Q12 mass to understand the amount of the genetic acid that has been grafted on this beta-lactoglobulin. So the results shows you the ratio between the genetic acid and the lactoglobulin ratio of 5:1. So this is very interesting. You can see here. So it shows us like the grafting is relatively random. So some of the results shows one adduct, means like there's only one genetic acid is grafted. Some of them we got 2, we got 3. So it's relatively random here. So the maximum we can get will be just 3 adducts for the 5:1 ratios. And then we also characterize the higher ratio one, so they can have like a 14 adducts maximum. And then we use the UV spectrum to further characterize these compounds. So you can see here on your left, so the blue one at the blue peak, the black peak around like a 330. So that's the peak for the genetic acid. So you will see a shooter generated from the synthesized compounds. So the zeta potential analysis is also very interesting. So the beta-lactoglobulin solution itself at pH 7, so the surface charge is around negative 10. So when we graft more genetic acid on the structure, so the magnitude of the zeta potential becomes like higher. So this is particularly interesting, and when we understand the mechanism later on their like emulsion stability using these results here. So after we fully characterize the structure and prove the successful grafting of the genetic acid on the beta-lactoglobulin, and then we use the EPR DPPH assay to characterize their free radical scavenging capacities here. So the graph on your left side, you can see the peak, the DPPH radical peaks goes down when we extend the TAM. And then we use the double integrate method to characterize the relative capacity of these compounds. We got the fitted curves, kinetic curves on the right side. So you can see like for the beta-lactoglobulin with 150:1 ratios of the grafting. So it has the best decay rate here, indicating it has the strongest free radical scavenging capacity. So when we extended the ratio to 300, actually it goes back to the less capacity. So this is particularly interesting because most of the time you will think like with more phenolic acid, you may have like a stronger free radical scavenging capacity, but this is not the case here. And we want to test if those like synthesized compounds will have a real protective effect against the oxidation in the real food system. And then we want to use the stripped hemp oil and water emulsions to test this. But very interesting, you can see here. So this is the physical stability of the emulsion stabilized by the conjugates here. So we use the ratio between like of the 30, 75, and 150. So we compared the particle size and the zeta potential of all those conjugates with the beta-lactoglobulin without modification. You can see the particle size of the beta-alg itself is way smaller than the ones emulsified by the conjugates. And also the zeta potential of all those of the emulsions stabilized by the conjugates is lower. And at pH 7, the stability of the emulsion can only last for 8 days for all those conjugates. However, for the raw lactoglobulin has way longer stability. So this will be even severe when we switch the pH to pH 3. So you can see here, after 2 days of storage, all the emulsions stabilized by the conjugates start to have a phase separation. And this is not very surprising because if you take a look at the size on the left side, so the size of the emulsions prepared by the conjugates is way bigger than the one without the phenolic compounds graftings. So this is very interesting. So we are working on this area trying to figure out what's the reason causing the instability of the emulsions prepared by these conjugates, so that we don't have any like oxidative stability results for this emulsion here. A little bit short conclusion for this part. So we use the EDC like NHS coupling reagents, which allows us to graft the genetic acid on the beta-lactoglobulin, and then we prove the successful synthesis of those conjugates through several techniques. So we found like the ratio, the genetic acid and beta-lactoglobulin ratio of 150 to 1 is the optimum ratio to demonstrate the highest free radical scavenging capacities. So we have a kind of the interpretation for the results. So we thought the grafting of the genetic acid on the beta-globulin could change the structures so that they can expose the antioxidant residues, for example, the cysteines from the beta-lactoglobulin, in addition to the free radical scavenging capacity from the genetic acid. So like I mentioned earlier, so food waste and food loss and food waste are the two major issues for the food sustainability. So start from then, we thought, is there any way we could create any like a dual functional ingredient that can combat both the microbial spoilage and the chemical spoilage? So with that in mind, we designed a third experiments, and then we thought we will try to graft the phenolic compounds on a natural antimicrobials, and then we choose the lysosome. So why we choose a lysosome? So lysosome is a natural and green antimicrobial, but its antimicrobial capacity is relatively weak. So the lysosome, most of the lysosome we use in the food industry is from the hen egg lysosome. So it has a molecular weight about like a 12 kilodaltons. So the mechanism for the lysosome to kill the microbials has been well established. Basically, so there are two amino acid residues, so glutamine at the 35 and aspartic acid at 52. So those two amino acids are very important. So they will form what they call like an alpha helix loop and helix structures, so that they can hydrolyze the peptide glycans of the gram-positive bacteria. And then so that they will form this, what they call the carpet-like mechanisms. So the damage the cell wall will allow the nutrients from the bacteria to leak out so that they can prevent the growth of microbials. So we use the same strategy as we did for the beta-lactoglobulins. We use the EDC and NHS coupling reagents. So on this hen lysosome, it has 122 amino acids. And among all those amino acids, there are about like there are 14 lysosomes. So that's why we designed a series of the feeding ratios from between the genetic acid and lysosome from 1428 up to 280s. And then we again use the several techniques to prove the successful of this grafting. And here is the result we got from the FTIR. As I mentioned, so this newly appeared absorbance occur again in this conjugates, proving that the genetic acid has been grafted on these structures. And then we use the FTIR, we use the UV spectrum, we found the same results. So with more genetic acid added into a system for the conjugates, we find this kind of the shooters going up here. For the zeta potential analysis, this is also interesting. So the zeta potential of the lysosome at the pH 7, so it's about 20. And we know like for the β-lactoglobulin, it is generally considered as an acidic protein, just because the pKa of the beta-lactoglobulin is about 4.8. For the lysosome, it is considered as the basic proteins. So it has the pKa around 11. So when we add more of the gentisic acid on the structure of this lysosome, so the zeta potential at the P7 becomes less and less. So basically, if you combine those two together, basically, just because this reaction uses the basic amino acid lysosomes, so that it has less of these basic amino acids available to be analyzed. And then we characterize the particle size of all those conjugates. We found at the lower fitting ratio, so when we have less of the gentisic acid in these conjugates, so their particle size is in the nano range. When we increase the amount of the gentisic acid, meaning like you have more gentisic acid to be grafted on this lysosome, so the particle size becomes bigger and go into the micro range. So the TM image also shows that. So the one on the very right bottom, you can see it's a significant aggregations for those conjugates. So that is the ratio of 280 to 1. So again, we want to see if the grafting of the gentisic acid could also improve the free radical scavenging capacity of the lysosome. So we use the EPR, DPPH assay again. So we had kind of the similar results here. So the blue line here, you can see the one with the highest decay rate. So that's the one at 120 to 1 ratio. With extra amount of the grafting, like a 280, so their scavenging capacity goes back down here. So like I said, the goal of this one is to create a dual functional bioconjugates that can both combat the growth of bacteria and also provide the free radical scavenging capacities. So then we use the Lister inocula as the model gram-positive strains, and we tested their antimicrobial capacities. So the result here is interesting. We found the grafting of the gentisic acid on the lysosome itself, they may remain the antimicrobial capacities. However, with the extra amount of the gentisic acid, 280, as you can see the plate here on the bottom, or on the right bottom here. So basically, it mitigated the antimicrobial capacity of the lysosome here. So it means from both of the research we found, like the ratio, the fitting ratio is very critical for this research, for the activity of the conjugates. So we know for the lysosome, basically it's a kind of enzyme. It's an enzyme that can hydrolyze the cell wall, as I mentioned earlier. So we tested the enzymatic activity of the lysosome and the conjugates. So we found the higher amount of the grafting. So the blue line on the very top, that's the one with extra amount of the gentisic acid. So it did decrease the activity of the lysosome. So which means the extra amount of the grafting could mitigate, could impact the functionality of the lysosome. And then we use the SEM to observe the morphologies of these gram-positive bacteria, and compare to the control and the lysosome treated the bacteria, we found like all of those conjugates, they could change the morphology of the strands. However, for the higher amount of the grafting, so 280, the one, so it has less agglomerization effect as compared to the one with the lower fitting rate. But I think most of the study, when they are done until this step, so they just get the conclusion. But we want to further understand what would be the reason, like when we have the extra amount of the grafting, what would be the reason to cause the loss of the activity for the lysosome? So by collaborating with my colleague, Dr. Yang, so he is the expert of the EPR. And we start to use a cutting edge technique we call the side-directed spin-label EPR. and to understand the molecular mechanisms of this kind of the changes for the lysosome. So this technique basically, so here I just gives you a brief introduction. So basically we want to introduce a radical side chain here, we call R1 here. So this R1 you can see has like a disulfide bridges. So basically this disulfide bridge can react with the cysteine residues on the protein backbone. So here I list the 4 different types of the EPR spectrums. So the first one, basically that's the radical pattern for this R1 groups. That's a superfin splitting for the R1 group. So the second pattern is the EPR spectrum for the free protein. So when the probe R1 is restricted on this protein, so you get a new patterns here. So that's a SERP pattern. So when this R1, it's a radical, so it will rotate. So when the rotation of this radical is confined, you get the pattern from of this as showing in this number 4. And using the simulation and program, so we are able to identify what's the component causing those types of the mobility and immobility. So this technique requires us to reconstruct the proteins, just because each time you can only introduce one R1 groups on this protein backbone, which means we need to create several like cysteines. So in the beginning, you need to get rid of the free cysteine on this protein, and then you will create the recombinant protein by the location you wanted to introduce a new cysteine. So the picture on the bottom here, the second one shows like recombinant protein. So you can see the blue dot there. So that's the position we purposely created for the cysteine, so that cysteine can interact with the R1 to form the third picture we showed. That's the site-directed spin labeling protein. So each time you can only, like I said, you can only create one cysteine mutant protein. So for example, for this one, so there are 8 sites we want to use to interact with R1. So in total, you will have 8 different types of the mutant proteins. So some of the details about these techniques you can find on the papers I listed here. So this is the kind of lysosome, a model lysosome that has been widely used. It's a T4 lysosome. T4 lysosome is a lysosome found from the T4 like a virus phage. So here I listed the amino acid sequence of this lysosome. So it has like a 13 lysin residues. So we want to know what's happening when we grafted the gentilic acid on this structure. So in that case, we need to create 8 different types of the recombinant proteins. So we call them like 44R1, 65R1 until 150R1. And on this side, you have a cysteine. So that's the created cysteine, so that cysteine can interact with R1 radicals. And then we will know the motion of these radicals to understand the structure changes. And then after we create all those like the recombinant T4L proteins, we use the same strategies, EDC and NHS coupled reactions to graft the gentilic acid on all those T4L proteins. Since, like I mentioned, they have the 13 lysyl residues. And just because we need to create that much of the recombinant protein, so we only focus on 2 like feeding ratios. So the gentilic acid to T4L at 28:1, and another one will be 280:1. So in order to probe the molecular change, like the structure changes of this protein at the molecular level, again, we need to create 18 T4L proteins. And then we interact with the gentilic acid. So in order to understand the structure changes of this protein, so we have 8 sites listed here, and with the 28 ratios, we create 8 different types of the conjugates. For 280:1 ratio conjugates, we also created another 8 conjugates. So the rest of the reaction conditions will be same as what we did for the Hen lysosomes. So after we create all those conjugates, we use the same method to characterize the structures. And here I just listed you 2 examples here. So we also found this newly formed the absorption band. Basically, that is from the hydroxyl groups on the gentisic acid. So it proves that all those newly created conjugates, so they have the gentisic acid grafted on their structure. So after proof the structure, we use the EPR to record the spectrums. So here I just listed all those spectrum for all those 8 conjugates. So you can see, so this will be the direct results. From these results, you can see as I highlighted on the first one, so that is the 44R1. Means we have the 44 position to be replaced by the cysteine. So the cysteine can interact with R1. If there's any changes happening in this area, so you will change the EPR patterns. So we see this, the highlighted the circle there. So that's the pattern indicating the immobility of this probe under that location. So the rest of them, so 65, 72 until 151. So all those locations, we didn't see huge changes in those regions. So which means, and we also found the higher ratio here. So although it's hard for you to see here, but we found a higher grafting ratio, a 280, because here we only did compare those 2. We found a higher grafted ratio, so they have the greater effect on the immobility of the probe on this position. And also we use the simulation programs to evaluate what would be the major components to cause these results, but I didn't demonstrate the results here. So go back to the structure of this T4L here. So from this T4L, so it has the similar mechanism, antimicrobial mechanism, as compared to the Hen lysosome. So remember, for the Hen lysosome, I mentioned they have the glutamic acid and aspartic acid. Those will be the very important 2 residues. For the T4L lysosome, at the 11th and this 20th, so they have the same. They have the 11th here. I highlighted the E, so that's the glutamic acid. D, that's the aspartic acid. So those 2 are very important for forming the cleave, so that they can hydrolyze the cell walls for the bacteria. So as I mentioned, the 44 here, the 44R1 from our EPR results, that position is highly impacted by the grafting. So which means the grafting of the gentisic acid will impact the structures, the molecular structures of the amino acids, specifically those cleaves on this region. So that is the reason why when we graft the phenolic compounds on this lysosome, so specifically the gentisic acid on this lysosome, it decreased their antimicrobial activities. So this brings us to the other researchers. We want to understand how the structure of phenolic compounds could impact their activity. So that is also an ongoing research in our group. So some short conclusions for the third part of the research here. We use the EDC and NHS coupling reactions to graft the gentisic acid we found on this lysosome, antimicrobial lysosomes. And we use different techniques to prove the grafting of the gentisic acid on the lysosome. And also we found the grafting of the gentisic acid did increase the free radical scavenging capacity of these conjugates. However, over dose of the grafting could decrease the activities. So the antimicrobial activity of these conjugates will be affected by the graftings. At the lower concentration, we found it can maintain the similar levels, but when you increase the amount of the phenolic compounds, so their antimicrobial activity goes down. So this is very interesting. So together, from all those three parts of the research we found, like soluble-bound phenolic compounds, they have a better antioxidant capacities against the emulsion oxidation. So this might be the very interesting and like a strategies for the future novel natural antioxidant identification. So we found like grafting the phenolic compounds, specifically the genetic acid on this β-lactoglobulin, and also the lysosomes. So the conjugates has a better free radical scavenging capacities. However, when you add extra amount of the phenolic compounds, actually it can decrease their free radical scavenging capacities. So the conjugates we prepared between the β-lactoglobulin and the genetic acid, they have relatively poor stability to stabilize the emulsions, especially at the pH 3. And we really want to understand what's the reason cause that. So the antimicrobial activity of the genetic gas conjugate lysosome was diminished, especially when we have a higher amount of the genetic acid. So here we have the questions that needs to be addressed in our following studies. So how can we protect the active site of all those bioactive functional proteins? For example, for the lysosome, how can we maintain the structure of those active sites so that they will maintain their antimicrobial activities? So that is the key for us to develop the dual functional proteins. But we are also trying to use different types of the biopolymers for the same purposes. So that will be all what I have to share with you today. But like I said, we have lots of ongoing researches from the findings we got from the current research. So please, like, if you have any questions, you can just take a look at our publications I listed on this presentation. So at the end, I would like to acknowledge all the researchers and my students, and also for my colleagues. So without their help, we cannot have such a great research findings. So I also would like to acknowledge AOCS, and again to offer me this opportunity to share our research, and also the financial support from the USDA to conduct this research. So at this moment, I would like to take any of the questions. Thank you so much.
Thanks so much, Bingcan. I do want to mention that I left a few things out of my introduction with Bingcan. I just wanted to mention that as a young scientist, he has a very impressive publication record with over 80 peer-reviewed research papers. And he's received several awards throughout his career, including the Thomas Mouse Memorial Fellowship, which he got during his PhD. And those of you who aren't familiar with this award, this is the top graduate student award at AOCS. And he's been very active since with AOCS and is currently the Secretary Treasurer of the Lipid Oxidation and Quality Division. So that was a great talk, Bingcan. I'll lead us off with the first question. It's very interesting that through these modifications, you are able to make the protein more negatively charged. And when you get that increased negative charge, how much do you think that impacts the antioxidant activity through its ability to chelate more metals? And my second part of that question is, does it change the pKa or the pI of the protein at all and help it maintain its negative charge at a low pH? Because I think one of the limitations of using proteins as chelators is they become positive at pHs around 4.5 or below.
For this question, I think it's really interesting. So we found for example, if you compare the zeta potential of the beta-lactoglobulin as a raw solution or after you like homogenize them. So you'll see there's a huge boost for the zeta potential. It's very interesting. And for our study, so when we chemically modify them, we did find the change, like the magnitude of the zeta potential becomes bigger. But those number is relatively lower than the homogenization treatment. So there must be something like contribute to the zeta potential of the protein. Very interesting. So like an example, it was in the beginning, it was a little bit frustrating for us because like I thought we developed this like conjugates. However, there's the role for them to prepare emulsion is getting worse. But actually, I think there are some like interesting things like behind that, which is the things we want to figure out. So specifically for the β-lactoglobulin, basically you just use the lysosome residue. So you shifted the pKa of the conjugates toward more acidic. So we don't have the data yet, but I guess the pKa of this conjugate will be close to 3. So that's the reason why at the pH 3 it has a very poor stability. So for the kinetic, for the methylating results, it would be a very interesting angle to think about. So the first, like at this moment, we want to create the very stable emulsion using these conjugates.
So a question that's come in is, what is the reason that the soluble bound phenolic compounds have better antioxidant activity in the emulsions?
Can you repeat one more time? So my speaker is not very good.
So what is the reason that the soluble bound phenolic compounds have better antioxidant activity in the emulsions?
That is really a good question. So we did a lot of research on that. We can only say that's the reason why we conduct our like a second and third research. So we, like I mentioned, we propose a kind of the mechanics to describe them. So we call like a dual effective function from this the conjugated form. So you got the two part of the effective from your compounds. One is from your phenolic compounds. It has a free radical scavenging capacities. The second one is from the one we really don't know if it. I think in most cases will be the polysaccharide. So you will get the effect from polysaccharide, or if it's a protein, will be from protein. So from the EPR results from the second research, we found the EPR or the decay, if it's by the exponential decay. So telling us there are two events associated with their free radical scavenging capacities. So you have a very sharp burst in the beginning. So we assume that will be from the phenolic compounds. And then you have a slow down decay. So that might be from the kind of the compounds they conjugated. So that is also the reason why we want to use this kind of a reverse thinking to prove this concept by grafting the phenolic compounds on different types of biopolymers. So definitely, like again, back to the question, Eric, you have for the zeta potential. By grafting these phenolic compounds on that, you think for this phenolic acid, it has 1 carboxyl groups, 2 hydroxyl groups. So the carboxyl groups will react with the lysine amine groups. So it changes the zeta potential. But I guess in the meantime, it will also change the structure of the protein as well. So that's why we assume like that they may expose some of the antioxidant residues like cysteine. So for the β-lactoglobulin, it has 5 cysteines, but 2 of them, so 4 of them forms 2 pairs. You only have 1 free cysteines. So maybe this like a modification could release some of those.
So during the production of the conjugates, did you come across any precipitation irrespective of the concentration of GA?
So that's kind of the thing we are thinking. So when we have like an overdose of the synthetic acid, we do find the precipitation as the conjugates. So that's why like we have another research, like we want to understand the physical interaction now between the protein and the phenolic compounds using the EPR method we have.
So that seems kind of unusual because the protein's becoming more negative. So you would think aggregation would be less. So any idea of the mechanism?
You say like become more elective. The reason become more elective, like I said, is like you just break down the balance between the ionizable group on the protein. So you use the basic amino acid residue, allowing more of the carboxyl groups to be ionized. So you think like you're right. Like if you tested the zeta potential, so for example, for the β-lactoglobulin one, so it becomes more elective. So you think it will be more stable, right? But when we make the emulsion, it's not like that case. But compared to the zeta potential of those conjugates with the raw β-lactoglobulin, you may get some idea because the zeta potential for the raw like β-lactoglobulin stabilized emulsion, it's very high. The mechanism is very high, 50 something. But some of the conjugates only have like a 20 around. Basically, they maintain their zeta potential before emulsification.
What would be the possible application for the dual functional conjugate in a real food system?
So that's a good question. So like I said, we want to understand the mechanism at this step. So that's why I use this kind of a chemical couplings. So the coupling reagent we use, so they are widely used for like a biomaterials synthesize. So the next step for us is to use like the food grade enzymes for this purpose. So if we are able to create, for example, our goal, if we could maintain the emulsification properties of the β-lactoglobulin, but in the meantime, we improve the antioxidant capacity for their use, so we can carry both properties for the same ingredients. So for the lysosome will be the same. So in the beginning, we thought like because like phenolic compounds, some of those are also showing antimicrobial capacities. So we thought we could bring both antimicrobial property from the lysosome and the free radical scavenger property from the gentilic acid together to get the dual effective ingredients. If we could achieve that, it would be very useful for the industry. So you can just use one compound to combat both the like microbial spoilage and chemical spoilage. So that's my long-term goal.
Another question. Why did you choose the ratio of 28 and 280 rather than 112? This is the license based on antimicrobial activity. It seemed that the ratio of 112 is the optimized ratio.
Yes, so that's a good question. The reason, like I mentioned, there are several reasons. Number one, in order to use the site-directed spin label EPR, it's very complicated. It's hard to create all those like the protein combinations. We want to find two extreme conditions, low, very low, and very high, to understand how those grafting could change the structure of the T4 lysosome at the molecular level. So that would be the major reason why we choose those foods. But we found like even for the 28 ratio, we still found the kind of the impact for the structures, especially at the active site of the T4 lysosome. So it proves like this grafting did impact their active site.
Okay, I think that's all the questions we have for right now.
Perfect.
So I would encourage, I'm sure Bingcan wouldn't mind if you have other questions, you could probably email him and he'd be happy to answer your questions.
Yeah, definitely.
And I want to thank everybody for attending and congratulate Bingcan a year late.
Thank you so much.
But it's still a very good day, and I'm really glad that we were able to do this.
Yep. Thank you, Eric. Thanks everyone for attending.